Welcome to this instructional video about boiling points of organic molecules. So when it comes to boiling point, it really has to do with self-association through non-covalent interactions. When you're considering boiling point of an organic compound, water does not matter. It's not dissolved in water. It is a pure sample of an organic compound. So how well do the molecules attract one another? That's the big issue with boiling point. Well, we've got some guiding questions to help us predict and to rank organic compounds based on boiling point. So the first question is, can the molecule hydrogen bond with itself? So imagine taking two copies of the molecule, if you will, and determining if they can hydrogen bond with each other. So the issue here is a molecule needs both the donor and an acceptor. It needs at least one donor and one acceptor in the molecule to form a hydrogen bond with itself. And if you ask that question and you come up with yes, then this tends to increase boiling point. So if a molecule can hydrogen bond with itself, then it will tend to have a higher boiling point, a fairly high boiling point. Okay, well, at some point we may have to come back to hydrogen bonding to break a tie. The next question is, how heavy is the molecule? So here's the deal. When I say heavy, I mean how large is the molecule? What is its size? If everything is a tie, that is, both the molecules you're looking at to rank according to boiling point can hydrogen bond with itself, and both are the same size, you may have to come back to boiling point, back to hydrogen bonding to break that tie. And so you may have to consider hydrogen bonding capacity and the balance of D plus A. So if two molecules are about the same size, they both can hydrogen bond with itself, then probably the one that has a higher D plus A will have a higher boiling point. If D plus A is the same, then the one that has a greater balance of D plus A will probably be the tiebreaker and have a higher boiling point. All right, so what about this size issue? Well, you know, the ability of molecules to self-associate can certainly happen through dispersion forces, and we know dispersion forces is a surface area phenomenon. And so the larger the molecule, and more specifically the larger the surface area that can exist between molecules when they associate, we will tend to have more dispersion forces. So a good way to think about this is, how large is the molecule? That is, how many heavy atoms does it have? And the number of heavy atoms is the number of non-hydrogen atoms. This is a rough measure of how large a molecule is. It's also a rough measure of, the extent of dispersion forces that can exist between two like molecules. So how large is the molecule? All right. Well, we got a rule. We have a rule here. As you increase the number of heavy atoms, in general, you will increase the number of dispersion forces between the like molecules, which will tend to increase boiling point. So the size of the molecule impacts boiling point. Now, in this rule, there's one big caveat, one big warning. It's like, okay, be careful with this. If there's branching, if the molecule has alkyl groups, hydrocarbon part, and there's branching in there, there's branch points, that's going to impact the boiling point significantly. So here's the rule here: branching of hydrocarbon or alkyl groups tends to lower boiling point. So these are things you need to think about. Can the molecule hydrogen bond with itself? How large is the molecule? And is there any kind of branching, any branched carbons in the molecule? So let's do some examples here. So we have a competition, methyl acetate versus propionic acid. Which of the two has a higher boiling point? Well, let's draw these molecules. The first one you will recognize as an ester. So it is methyl acetate. So let me draw this a little bit more to my liking. And of course, we're going to put in lone pairs because that's what we need to do. This is just a little bit of nomenclature practice. Everybody loves that. So this is methyl. And then this is derived from acetic acid, so we call it acetate, methyl acetate. So the other molecule is propionic acid. Clearly from the name, it's a carboxylic acid. Pro means 3. So here we go for this molecule. Going to be a good accountant of electrons. Put in the lone pairs. Oh, there we go. So here we go. Sometimes we do the size issue first. So let's just look at this. So how many heavy atoms in each of these molecules? Well, the number of heavy atoms in methyl acetate equals 1, 2. I'm counting non-hydrogen atoms. So carbons and oxygens in this case. 1, 2, 3, 4, 5. In this case, the number of heavy atoms is 1, 2, 3, 4, 5. So they are the same size. So dispersion forces is not going to be an issue here. This is probably going to come back in some way to hydrogen bonding. And so let's ask that first question now. Can methyl acetate H bond with itself? And the answer to this question is a resounding no. There is no donors in methyl acetate. You cannot form a hydrogen bond between two methyl acetate molecules. And that tends to lower boiling point. So here we go. Now, propionic acid. H bond with itself. I say yes. There is a donor and there are 4 acceptors. So this molecule can, if there's 2 copies of it, form hydrogen bonds with itself. Clearly, the winner of the boiling point competition between these 2 molecules is propionic acid. And so here's a general rule for you. Okay, if molecules are the same size, one's a carboxylic acid, one's an ester, then the carboxylic acid will have a higher boiling point because carboxylic acids can hydrogen bond with themselves and esters cannot. I'm just giving you that rule as a mindset to be thinking about all kinds of organic classifications and boiling point. All right, well, the one down here, we need the highest boiling point between hexane, pentane, or 2-methyl-butane. It looks like to me, based on the name, we have 3 alkanes. And so hydrogen bonding is not going to play into this analysis any way, shape, form, or fashion because alkanes can't do hydrogen bonding. So this is going to be a dispersion forces issue. So let's think about the size. Okay, how many heavy atoms in hexane? Well, there's 6 carbons in hexane and the rest are hydrogen, so 6. What about pentane? The number of heavy atoms equals 5. What about 2-methyl-butane? Be careful. Some people would want to say 4 right away because of butane. But remember, it's 2-methyl-butane. So that would be also 5. So right away, I don't think we have any trouble here saying this is the highest boiling point hexane has the highest boiling point. Now, we have two more. They are the same size. Hydrogen bonding is off the table because neither one can form hydrogen bonds. Then we're going to have to use our branching rule. 2-methylbutane has a branch point. Branches tend to lower boiling point. So 2-methylbutane will have the lowest boiling point. And the pentane here will have a boiling point somewhere in the middle. So, I hope this has been a useful video in terms of boiling point of organic compounds.